All right, so we've done the first part of the lab, okay? And we have our tablets crushed, sitting in water, heated, helping them hydrolyze into the two acid components. We have made our decisions on our excess chemical. We made a molar concentration of 0.4305, at least we thought it was. We made 100 milliliters of it. Then we tested it with KHP and found that it's actually 0.387. Okay, now we're gonna now do some other calculations to figure out how much acid we want to make backwards, but we're gonna have to do some recalculations here, okay? Now, we decided that we wanted to have excess 0.01722, the total value. We thought we could use 40 milliliters of this 0.405 solution. Well, because it's what? Because it's weaker, okay, we're gonna need a little bit more, okay? So just be careful. So let's go figure out exactly, just for fun, exactly how many milliliters of our base solution, which we've made already in the part one, okay, how much of this do we need, okay? We thought we would need 40, okay, but we're gonna need more because by standardizing it's less. So I'm just gonna show you exactly, when we actually do the lab, let's figure out exactly, we still wanna keep these numbers constant, so instead of using 40, let's go calculate exactly what we should have. So when I do that, I'm gonna stay with my target values that I started with. We made decisions in this lab that we wanted to have a total excess of 0.01722. That stays the same. So think about this. We have the molarity. We know it's moles over liter. And the new molarity that we just found is 0.387. So 0.387. Okay. And we know that we want to add exactly that many moles of hydroxide. That goes on top. So 0.01722. We're going to solve for the liters that is needed to deliver that many amount of moles using that concentration. It's going to be above 40 because our concentration of the strong base is a little weak. So we're going to solve for that. And if you do your algebra, liters is equal to 0.01722 moles over the 0.387 mole per liter. Obviously, moles cancel. 1 over liter is going to give you liters. So what is the liters needed to deliver that? What is the exact value? So if I do 0.01722 divided by 0.387. What is that? 0.387. So it's 0.01722 moles. That's our total excess, our total amount of hydroxide. It includes the excess, sorry.
I got 0.044.
Ah, makes sense. 0.044?
Yeah.
What's the third digit?
4.
So it's point, they're all, it's
0.0445.
Okay, 0.0445. Okay, so when I convert this to milliliters, right, times by 1,000, it becomes 44.5 milliliters. That's exactly how much of this I need to measure into my what? Beaker of dissolved, okay, aspirin that's been heating, okay? It is bigger than the what? 40 milliliters that we calculated for because we suggested we were going to have that concentration, but by standardizing. So it's really important to standardize. We'd be off by a significant amount there. So we're going to keep that to the side when we do that lab now. Now, where are we in this lab? When I drop 44.5 milliliters of base into this acidic solution, I'm going to go past the target amount that we expect, and we're going to be here now. We're going to have some excess, what? Hydroxides. So we want to titrate back with strong acid. We're going to use hydrochloric acid. So now we have to design a lab. How strong of hydrochloric acid should I make? Okay, we don't need this anymore. Okay, but now we need to figure out our solution. Okay, well, we see by an arbitrary decision of student L, she decided that the target means that this is what we expect if the tablets are 325 milligrams per each. We've done the stoichiometry. So the excess should be 0.01. So we want to deliver 0.01. We want to deliver 0.01 moles of H plus. Okay. How many milliliters do you want to add to do that? 50? 40? 100? Let's stay with, let's see, I have a 25 milliliter. I have 25 here. So let's do 25 since I have a 25 milliliter graduated cylinder. I mean, you can decide anything you want.
No, I'm good with that.
Okay. All right. So look at this. What is molarity? Molarity is moles over liter. We're going to use and dilute to 25 milliliters because I have a nice, precise graduated cylinder that goes to 25. And because it has to be liters, it's 0.025. Someone do the math for me. What's the molarity that I have to make? 0.00025. Is that correct? 0.01 divided by 0.025?
Oh, we're doing division.
Yes, I don't think so.
0.4.
Yeah, I thought so. Because we're dividing, yeah. So 0.4 molar. Okay. So give me some more sig figs there.
It was like just 0.4.
Okay, 0.4, 0.40,
Yeah.
0.401, or just, it's 0.4.
0.40.
Yeah. We wear gloves in this lab because that sodium hydroxide, you get on your skin, it can irritate your skin. I got some on my hands, and I wipe my temple, and my temple is irritated. Okay, so here we go. And where'd my glasses go? Is it over there? Gotta end it. Okay. So we got 0.4 molar, 0.40, okay? That's the concentration we want to make. So we have 0.40 molar HCl we want to make. Okay, now, unlike the NaCl, the NaOH that we made, we're going to use a stock solution. This I got from a company. And it's verified to be, right there, 1.0 molar solution. So we're going to use the dilution formula. And here we go to do this. MV equals MV. So I'm going to start with the stock solution, which is 1.0 molar. The question is, how much volume do I need of that to make a new solution that's 0.4? Okay. And how much do we want to make? It's always a good question. How much do we want to make? We want to make 25. Let's keep that in liters, so 0.025 liters. You don't have to if you do this proportion, but I just do that. So, let's do the math. And when you solve for the question mark, it's 0.4 times 0.025. We should know that's moles. Of course, silly, but divide by 1.0 molar. So what do you get when you times 0.4 times 0.0425?
0.0425?
0.025.
So 0.4 times 0.025, and I need to plug in.
I got 0.01.
0.01. Everyone's confirming that? Those at home. Okay. Okay, I've got to plug this in because they're losing. I don't want to lose the video here. Okay. So we solve for this, and we get what?
0.01.
Okay. 0.01 liters is needed. And what does that mean? 0.01 is what? 10 milliliters. So what this means when you use this equation, You need 10 milliliters of a 1.0 molar solution. You measure out exactly 10 milliliters. And then you do what? And then, party people, you dilute. Okay, you dilute to 25 milliliters. So what we're going to do is we're going to start and measure out 10 milliliters of the 1.0 molar solution. And then we're going to dilute, we're going to add water to the 25 milliliter mark. That's how you use that formula. So you guys are going to do that now. So here's your 1 molar. We have our gloves on and our goggles on. Okay. We're going to use this graduated cylinder here. It's got a 10 mil mark. You can add by pipette. And that's all we're doing very carefully. Okay. Again, the accuracy of this lab. Oh, she's a good pourer. Get a little below the 10 and now use the pipette. Get an eye level to get that meniscus right on that 10-0 mark. Okay, making solutions is very, very methodical. Whole lab depends upon how well you make your solutions. Okay, I've added some. Okay. Oh, sorry. What's your
almost
good? So, adding the 10 milliliters.
Does that look good? Yeah. Okay.
Good. So we have right now our 10 milliliters right there of our 1 molar, and now we're going to dilute to 25 milliliters. So now you're going to carefully add water to the 25 milliliter mark. I would get close, and then we're going to use a new pipette because the pipette you used has the 1.0 molar acid, so the pipette you need now should be clean. Use the water. Okay. There it is. Now just pipette again so the meniscus is right below, right on that 25. Very, very careful, methodical. Eye level.
Almost there. Maybe like 3 more. Does that look right, or does it still need more?
Maybe a couple more. Like 2.
Right to that 25 milliliter mark.
That's what we do.
Yeah.
All right, good. Now, you don't have to mix that. All right, now. All right. So, now, we probably should make more. This is where I just made a mistake, but we should probably make another one because we're going to titrate. That's exactly how much we need, right? Let's make one more like that. Okay, just to have enough. I was thinking the Tums lab for a second. So let's do one more. So we really should have made 50 milliliters to have excess. I'm sorry for that. So let's do one more like that. Okay, so that we have enough to fill a burette. Because we said what, 20, we said 25 is the target. So let's do
Yeah.
that again. Okay, so you're gonna add 10 milliliters, okay? Now, while you're doing that, okay, we can get to the other part of the lab. Okay, so you're making another, so we have 50 milliliters, that's my bad, we should have decided that. So again, the reason why I just decided to do that is that I didn't think about the next part. We're gonna titrate with the hydrochloric acid. 25 would be the target, we may need more or less, okay? Any case, so she's gonna make 50 by doing that again carefully. All right, so student M, okay? We need to measure out, okay, because right now, where are we in this lab? All we have is the what? The crushed tablet sitting in water. So what we're gonna do now is we're going to add the excess. And we're gonna add an excess of what? 0.01722 moles of hydroxide. And we just figured out that we need exactly, okay, 44.5 milliliters. So I'm gonna give you a graduated cylinder, another pipette, and you're gonna measure out 44.5 milliliters of the base solution. All right? Yes. And that's gonna just, so let me give you a graduated cylinder. You're gonna do the same thing. So you need 44.5. So you need a bigger graduated cylinder. Let me get that for you. And a clean pipette. We're almost done. Tedious is the key here, but methodical. So you're gonna measure out the base that you made, that's been standardized, and carefully it may get 44.5. We calculate that's how much of the base we need to rip past the end point so that you guys are in this position. Okay? And you're getting good at this. Okay? Now, what we're going to do now is just keep that. Okay? And we're going to pour both. We're going to keep it like that.
Okay.
All right? All right. Now, once Evan measures that exact amount and make sure he pipettes that, he's going to add. Well, he could be Evan because he's student E, but he's going to pour all of that in, okay, into that beaker that has the heated amount of. Yeah, gotta turn that, and we're almost done. So you can see the preparation is intense in terms of all your decisions, how they change when you standardize. But we're almost there, okay? Now, what are you taking out? Not water, right? Just the pure base?
Yeah.
Okay. Put that in a waste beaker. Don't put that back in your reagent bottle.
This?
So no,
Oh.
put that in a waste beaker. Anything you're taking out. Okay, you're just putting it back. Okay, good man. So he's measuring exactly 44.5 milliliters. Another, okay, tedious measurement to make sure you have exactly the moles. And some people would titrate this out of a burette separately. That's probably a little more of a precise way to do it. But if you spend the time and you're doing what student E is doing, okay, you'll get very good results. I expect to be plus or minus 1 of the milligram tablet on the bottle here. Okay, we expect that whatever Bayer says, 325 per tablet, that's what we're going to get. Okay. All right, now, once Evan is done measuring that exact amount, okay, we're going to now put that beaker, so student L, put that beaker on the magnetic stir, and I'm going to give you a stirring rod,
Okay.
okay?
The one that's on the hot plate?
Yep. It should be, hold on, careful, it is going to be warm. I'll move it. Last thing we want to do, oh, you just put it there, you're good. Okay, we're going to throw in a magnetic stirring bar, and you're going to turn that, mix that.
That's hot.
Yep, and there might be some precipitates in there. Don't worry about that. Yep, let's stir it up. Get it going a little faster. A little more aggressiveness. Good. All right. All right, so student E, take that graduate cylinder. Okay, hold on, because we want to see it, because we're out of frame here. Okay, cool, cool. Now just pour it into that beaker. We're adding what? No, we're adding it to the beaker. That is strong base. Into the beaker, into the beaker, into the beaker. That's a beerette. That's a beerette. The beaker. Okay? Don't forget what we're doing here, guys. We have a weak acid of aspirin that's been heated to expose and hydrolyze itself into the. Now you're going to add excess base right there. What we're doing right here, okay, for those at home, we're adding exactly 0.01722 moles. We just calculated all that stuff. Okay, now do it. Pour it. Pour it. Yeah, all of it. Good. Now, wash it out with a wash bottle.
Wash this out?
Yep. Okay, that's okay. Just the sides. Rub the sides around. Kind of. Yeah, definitely try to roll it around to just any remnants of OH minuses. We're going to do that. Okay. Good, and then pour it back in. So that any remnants, normally what we'd do is we'd wash the sides like this, right? We would kind of shoot the sides around. Yep, that's okay. Now pour it back in there. Now because we're almost to the top of that beaker and we're going to add more volume, I'm just going to pour this into a bigger beaker. And just to make sure that I got all of my data, I'm doing the same thing. I'm just washing the sides with the wash bottle. And I'll do that one more time, because you seem to be getting to the top of that beaker. Okay, so now what did we just do? We just got to this point, we overshot our projections with the excess amount. So now we're here, and now we're going to titrate back. So we have base sitting in this beaker. Stay with me, we're almost done. So what we're going to do is open this up, and just dump it out. Dump that base.
Okay.
Yep. Just open this up and let it dump. Okay. We have our solution of hydrochloric acid. Okay, I think we want to actually mix it a little bit. And what we're going to do is carefully add our hydrochloric acid into a volumetric flask. We should have done it this way. You can say what a bad chem teacher I am online. But all I'm doing is adding those 25, make her 50, should have made 100, but okay, it doesn't matter, because I'm mixing them now, making sure they're all mixed. I'm turning them, and then we're just mixing hydrochloric acid solution. So this is what student L did. She measured 225 values of them, and we made 50. Okay. We only going to need, what was the projection? We calculated that we wanted to use what? 25. We have a burette here that holds 50, okay? So right now we're going to use some of it to wash out. Okay, so now in this is what I need. Once it empties out, and it is empty, I need student E to take my acid solution and just rinse. Okay, open this up, now pour about 5 milliliters. Okay, so don't stand over stuff, stand on this side, and add that. The reason why we're rinsing is because that had base in it.
Wait,
So
you want it closed?
I want it open. I want it to run out to wash it out.
5 minutes?
Yep. We have more than enough. We only need 25 of it. A little bit more. A little more. All right, good.
Good?
Yeah, is it opening? Yeah, now it's opening.
Oh, all right.
Give me some more, because I think we didn't wash the sides a little more aggressive. All right, good. So we're rinsing out the burette with our titrant, because we had a base in there if we were to put the acid where the base was, we would be diluting, okay, our H plus. Okay, so anytime you're putting a new titrant, you should rinse it out. Okay, now let's add everything there. Add the entire amount of HCl there. It won't be to 50, so put the entire amount, let's close it off. Let's add the rest of it. We only need 25, so we should have more than enough. Okay, pour that in all the way to the top. Don't overfill it, let it go down, good. We get every little drop because we may need it. Good. Okay. So now where are we? Now we're going to titrate back. We want to figure out, okay, exactly how many moles of HCl. So we need the volume. Now we could use an indicator, but I want to use the pH probes. Make a graph. Okay, so Evan, could you please put that pH probe into the solution so it doesn't get in the way of, student E. I couldn't keep it going.
Maybe named Evan.
Yeah, it could be. Okay, formerly known as. Okay, all right. Yeah. All right, so what we're going to do now is we're going to put that pH probe in the solution that we're testing. So I'll help you with that. Okay, so you're all set up here. Okay, and I do want to put it into a buffer solution of 7. I don't really care that the pH probe is exactly calibrated because all I'm looking for is not the pH, I'm looking for the equivalence volume, but I'm just making sure, okay, that our pH probe is somewhat working. Okay, I think we're good here. Okay, now, we're going to put the pH probe in a solution. It should be acidic. No, it's basic, right? I'm sorry.
Yeah.
Didn't we overshoot
Yeah.
the solution? Yeah, we added excess base, so it makes sense that it's basic. So we're going to start high and go down. Okay? Now we could use indicator here. Problem is that the indicator is going to be purple and we have to stop it when it goes clear. Sometimes people do that. We're going to use the asymptote. All right. So you have about 11. Okay? The actual amount is we're going to say 11. It's on 11.00. Write that down. It's a starting point. Okay? All right, we're almost done. Okay, we're going to do this like we did our other titrations. We're going to add 1 milliliter at a time. Okay, student E. Okay, someone click on the green button.
Are we doing one by one?
Yeah, hold on. And now click the keep, don't do anything yet.
This thing?
Yep, and type in 0. Good, hit enter. Okay. Now, student E, formerly known as Evan. Okay, what you're going to do now is you're going to let out 1 milliliter.
One.
And let student L know you've done that.
Good.
And keep going.
Good.
And we should be, this is what's going to tell us our equivalence volume.
Good.
Oh gosh, I wrote 44.
I just changed that. Hold on. Just type it over here. Type it over here. Don't add any more. Hit cancel. Okay. Type this number over here as number 4. 4. Go backspace. Enter. Good.
10.
Here we go.
Good. Good. Good.
Good teamwork here.
Good.
Remember, we expect 25. We're only at 5, so.
Good.
And again, we do expect that the tablet
Good.
will say what it is. So I do expect that we'll get
Good.
around 25. Through all of this hard work.
Good. So
stop at 25?
No, just keep going. We want to see that asymptote. We want to see that sharp drop and find that equivalence volume on the computer graph.
Good. Alright, this should be it now. Stay on.
We haven't added 25 even close yet.
Oh.
You may say 25 because you
You
didn't
don't
start
want
at 0.
16?
Yeah.
Oh my.
Yeah?
Yeah, it's good.
Why is this not?
Good.
Oh,
Can you just move now?
yeah, I can.
Thank you.
Sorry, we just moved you.
Good.
Oh, it's starting to drop a little bit.
Good. I'll keep it in there. Good. Good.
Around 20.
Good.
It's starting to show its exponential change, I think.
Good. Good.
The key here, if we get to 25 exactly, and it's on an asymptote,
Good.
we know the tablet already is, oh, there it is, it's showing itself, it's jumping.
Good.
Look at that, we're getting there.
Good.
There it is. There's our asymptote.
Good. Good.
A little higher than 25, but
Still close. It's good.
shows us that our tablets are pretty close to what they say they were going to be. They keep going till we level it out. All that work, guys, and look what this means.
Good.
We're close to that 25 magic mark.
Good.
Should be leveling out now.
Good.
Good job. Keep going and level it out. Beautiful titration curve right there.
Good. Good.
And now it's going to start approximating the strength of the acid, right?
Good. Last one. Good. And empty it out.
Okay, stop right there. Hit the red button, the black button. Good. We're going to print these out.
That's fine.
But where is our, I would say between this line, which is at 26, to this line at 32. So where's our midpoint? Would you say 29.5?
Yeah.
Is I doing that right? Yeah, so
Yeah.
29.5 is your equivalence point. So 29.5. Guys, we have everything we need to finish this lab. 29.5. So cool. So let's do it. Let's get to the bottom of this, of this lab right here. Okay, we have a few minutes. I can finish this maybe, if this would, get your calculators ready. So we found 20, what did I say it was? What was the 29.5. Okay, milliliters becomes 0.0295 liters. That's how much, what? That's how much acid I had to drop. How many moles was that? Okay, what was the concentration we made? What was the concentration we just made?
0.01.
We made a solution that was 0.4, right? 0.4. So we times that by 0.4. It's a molar. Molarity times liters equals moles. So what's 0.4 times 0.095? Okay, that's moles of what? H plus we just added. Hey, that's equal to the 0.0118 moles of hydroxide excess.
Yeah.
Right, so back to our original values here, if you've been hanging on. Okay, so party people, let's get back to this. We added 0.1722 moles. We titrated back 0.0118. Okay, so what's the difference? This arrow, so let's subtract. So 0.01722 minus 0.0118, what's that value?
.00547.
Yes, that, my friends, is the moles of what? That's the moles of hydroxide that was needed to neutralize your aspirin. So let's do the stoichiometry. Okay, 0.00542 moles of hydroxide. Hey, what do we know? Isn't there 2 moles of hydroxide needed for 1 aspirin?
Yeah.
Yeah. So I divide by 2. I got moles of aspirin. Let's get the grams. Well, for every 1 mole of aspirin, that's 180 grams. So let's go find that number. 0.0052, divide by 2, times by 180. What's that value? .00542, divide by 2, times 180. 0.4878 grams. We're going to divide by 2 because there was 2 tablets. Divide that by 2. What do you get? 0.2439. We times that by 1,000, and we get, essentially, because it's milligrams, we get 244 milligrams. Okay? And that is your value for what's in that tablet. Okay? Target was 320. You got 244. But that's what our titration shows. And that is very possible. Okay? So we're under about 80 milligrams than what this is saying. I'm interested to see what that students get, but there it is right there. Okay? That's your lab. A lot of work there to get to that point. Oh, a lot of work to get to that point.